Hello, and welcome to this part of the FAST tutorial series. In today's video, we'll be looking at how to use the features that we extracted using the feature extraction module to generate a statistical model of our dataset, which will then be used during the tracking stage of the FAST pipeline. So to access the tracking module, this button should have turned green after we have completed the feature extraction module. So just click on it, and you should see this window pop up. And it's important to note that this window is split into two separate sections. So we have this section at the top here, which is what we're going to be focusing on today, which is where we create this statistical model of our dataset. And then we have this tracking section down here, which is where we actually perform the tracking based on the information that we've extracted from our dataset during the model training stage. So today we'll be focusing, as I say, on this training section. And you'll see that we have at the top here this list of different checkboxes that correspond to the features that we extracted in the previous module. Now, the reason that these boxes are present in the tracking module is that FAST uses a algorithm that allows us to optimally integrate information from many different features to improve our tracking performance. So, to give you some idea of the basis of the tracking algorithm, we assume that all of the different features that a cell or object possesses remain fairly static throughout time. So for example, if a cell is of a specific length, then we expect that the length of that cell shouldn't change between one frame and the next. If it does change drastically, that suggests that something has gone wrong. Either the cell has divided, or alternatively, perhaps the cell has moved out of frame, or perhaps the cell has been missegmented such that it is now broken into several fragments. In any of these cases, we want to avoid assigning a link between the previous frame and the next frame. So we can apply that kind of thought process to all of the features that we extracted in the previous module. And what we're going to be doing during this model training stage is performing a combination of machine learning and using a framework which is based on information theory to optimally figure out how to weight these different features and shift our feature space such that we can apply the data from all of them optimally to improve our tracking. So as that kind of argument suggests, we want to increase the number of features available to improve our tracking accuracy. So we'll just check several boxes here, length, area, orientation, width. We may as well just use all of the information available. Here I've just clicked on the channel selection box, which allows us to use the fluorescence data that we extracted in the previous module. I'll gloss over these two options for the time being, but here I'll come down to this box here, which contains two radio buttons. And what these radio buttons allow us to do is to choose which features we're going to use during this model training stage. Now it's important to emphasize that there are two separate stages at work here. So in the first stage, we're performing a kind of basic tracking, which is going to be fairly low accuracy, but is going to be used to provide the statistical basis for performing the main tracking stage, which is where we use all of this information together and cleverly integrate it to optimize our tracking fidelity. So during this first training stage, we have less information available to perform that tracking accurately, and so we want to use only those features which are very robust. Now in this case, what we can do is we can select only the centroids, which are typically the most robust of the features. And then we can alternatively use all the features if this doesn't work. So if we use all the features, then all of the features that we've checked here will be used during the training stage. Whereas if we check this one, then only the position will be used during the training stage. It's a bit subtle what the actual function of this is, so if you don't fully understand what's going on here, don't worry, just click only centroids and that will work 99 times out of 100. But for some particularly challenging data sets, this can be a good option to choose. So now that we've clicked only centroids and we've selected our features, I will click calculate, and that will now perform the model training stage. So you can see here that we've updated this box here with a histogram containing what's called our unnormalized step sizes and also this, our trackability plot. So as I mentioned before, in this initial model training stage, we're performing this low accuracy tracking, which allows us to generate the data set. And so when we perform this low accuracy tracking, we're going to create one population of links between frames that are going to be correct and one population that's going to be incorrect. And when we're generating this model, we want to ensure that we're only using those links that are correct rather than the ones that are incorrect. So this slider here allows us to move this red line, and what this red line is doing is it's splitting a population of links that we're going to count as correct, which are to the left, and a population that is incorrect, which is going to be to the right. And so the reason that this is kind of working, you can see that these step sizes correspond to small degrees of motion. So if you have low degree of motion, it's assumed to be correct, whereas if you have a large degree of motion, it's assumed to be incorrect. And so you see that there's this valley here which provides a nice point of separation between these two separate populations. So I'm just going to move this slider until that's splitting these populations in two. I also have up here the trackability plot. So this tells us how easy the data set seems to be to track over time. And if I now go to this video here and just compare, say, at the beginning, so you see that there's relatively low number of cells and a relatively low amount of motion. Compare that to the end, where there's a high level of motion and a very high density. You can see even by eye that this is much harder to track at the end of the dataset than at the beginning. And so what this is doing, this trackability plot, is it's using this information theory based metric to measure and quantify exactly what the difference in the ease of tracking is between these different time points. So here at the end you can see it's thought to be much harder to track than at the beginning. And you can read more about that in our preprint. So as you can see, this is falling down very low past frame 100. As a rule of thumb, I personally regard anything below 5 bits per object to be too noisy to actually use. So I'm going to reject everything past frame 100, which is roughly where this cutoff happens. So I can use these edit boxes here to limit myself to a specific subsection of the dataset, and then I need to recalculate the model. And so you can see here at the top that we have now isolated only the first 100 frames of this dataset. You can also see that the position of this valley has changed. That's because we have slightly fewer tracks available, slightly less data available because we've rejected those 50 frames at the end. So I'm going to pull this slider up until it's back at that valley position, and then recalculate. As you can see that the trackability plot has changed again, but everything's mostly above 5, so I'm relatively happy with that. So in the next video, we'll see how we can use this model, which we've just trained, to generate accurate tracks of our entire data set. So see you there.